Hey everyone, welcome to my YouTube channel. In this video, I will show you how to create and train a convolutional neural network using Python and the PyTorch library. To install PyTorch, you can visit pytorch.org. Under the Install PyTorch section, you can select the appropriate options based on your system, including your operating system, the package you want to install, the programming language, and the platform you want to use. If you have a CUDA-capable system and wish to use GPU as an accelerator, choose the latest CUDA version suited to your machine. If you prefer to use CPU for training your model, select CPU instead. Once selected, copy the command generated by the website and run it in your Jupyter notebook or command prompt. So now that we've installed PyTorch, we're ready to start coding. First, we import the Torch library, which is the core PyTorch library for deep learning. Then, import the neural network module, or NN, from PyTorch. It contains pre-built layers, loss functions, and other components to facilitate the construction of neural networks. This line imports the optimization module from PyTorch. It includes various optimization algorithms like SGD or ATOM that are used to train neural networks. The Torch Vision library is a part of PyTorch and provides datasets, models, and utilities for computer vision tasks. This line imports the Transforms module from Torch Vision, which is used for image preprocessing and augmentation. It allows you to define a sequence of transformations to be applied to images before feeding them into a neural network. Then we import the data loader class from torch.utils.data module. The data loader helps in efficiently loading and iterating through datasets during training. Finally, we import the pyplot module from the matplotlib library. Matplotlib is a widely used library for creating static, animated, and interactive visualizations in Python. Now let's create a PyTorch device object. It checks if a CUDA-enabled GPU is available using torch.cuda.isAvailable. If a GPU is available, it sets the device to CUDA, indicating the first GPU. If not, it sets the device to CPU. Let's print the chosen device. As you can see, it printed CUDA 0, since I have configured PyTorch to use the GPU while installation. Now we're ready to load the dataset. The dataset I'm going to use is the MNIST. The MNIST database is a large database of handwritten digits that is commonly used for training various image processing models. The first line downloads the training set of MNIST. And the second one downloads the test set by setting the train argument to false. Here, passing toTensor method to the transformer argument applies the toTensor transformation to convert the images from PIL images to PyTorch tensors. This transformation also normalizes the pixel values to be between 0 and 1. Alright, let's see what one of the images looks like. Each element of the dataset is a tuple of the input image and its label. we can see this image is handwritten 2, so the label assigned to it is obviously 2. Now it's time to create a data loader for the training dataset. We specify the batch size as 64. And shuffle through means that the data will be randomly shuffled before each epoch. Shuffling the data helps prevent the model from learning the order of the training examples. We also create a data loader for the validation dataset. Similar to the training loader, it also uses a batch size of 64, but shuffle equals false indicates that the validation data won't be shuffled. Typically, validation data is not shuffled to evaluate the model on a fixed set of examples for consistent performance assessment. Now, we can iterate through these data loaders to get one batch of data at a time. Let's check the dimensions of a single batch from the training set. As we can see, the first element is 64 28 by 28 images, and the second one is the corresponding 64 labels. It is worth mentioning that on PyTorch, the default memory format is channels first. It means that in a specific tensor like image, you would have channels, height, and width, and the channels are in the first position of a tensor. So you need to convert your input images to channels first format. Here, the toTensor method we passed earlier to our dataset objects has taken care of this. So, it's time to create our CNN model. We define a class called simpleCNN that inherits from nn.module, the base class for all neural network modules in PyTorch. The constructor method of this class is where we design and implement our network's architecture. First, we call the constructor of the parent class, or nn.module, to initialize the module. Then we create the layers of the network. I'm going to create two sequential layers called layer 1 and layer 2. Each consisting of a 2D convolutional layer or nn.conv2d. Followed by ReLU activation function, and then a 2D max pooling layer. These layers learn hierarchical features from the input image. Let's see how convolution works. In PyTorch, the conv2d method is a class that implements the two-dimensional convolution operation for neural networks. This operation is a fundamental building block in convolutional neural networks, or CNNs. The conv2d layer applies a 2D convolutional operation over an input tensor, typically representing an image. The forward pass of a conv2d layer involves sliding the convolutional kernel over the input image, computing the dot product between the kernel and the local input batch at each position, and producing an output feature map. The weights or parameters of the convolutional kernel are learned during training through backpropagation. Here, in-channels argument is the number of input channels. For an RGB image, this would be 3 red, green, and blue channels. For grayscale image, it would be 1. Out-channels argument is the number of output channels or kernels. Each kernel learns different features from the input. Increasing the number of output channels increases the capacity of the network to learn more complex features. Kernel size is the size of the convolutional kernel or filter. It specifies the height and width of the 2D convolution window. A kernel of size 3, for example, means a 3 by 3 filter. Stride is the step size used when sliding the kernel over the input. It determines the amount of movement between consecutive applications of the filter. A stride of 1 means the filter moves 1 pixel at a time. And padding is added to the input data before applying convolution. It helps preserve spatial dimensions and can be used to control the size of the output. A padding of 1, for instance, adds 1 layer of zeros around the input. Max_pull_2D is another important operation frequently used in convolutional neural networks, or CNNs. It is employed for downsampling or subsampling the spatial dimensions of an input tensor, helping reduce computational complexity and focusing on the most important features. Max pooling operates independently on each channel of the input tensor, taking the maximum value from each local region. The idea is to capture the most important features from each region, while discarding less relevant information, leading to a more compact representation. Finally, we create the fully connected layer or linear layer responsible for the final classification. It takes the flattened output from the convolutional layers and produces output for each class, 10 classes in this case. Now we need a method called forward. This method is responsible for the forward pass of the network. It specifies how the input X passes through each layer in the network. First, the input passes through the first convolutional layer. Then, the result from the first layer is passed through the second convolutional layer. Next, the output is flattened into a 1D tensor to be fed into the fully connected layer. And lastly, the flattened tensor is passed through the fully connected layer to get the final output. Our model is ready. Let's create an instance of the simple CNNs class and move it to the specified device, which in this case is GPU, using .toDevice. Now it's time to train the model on MNIST dataset. We're going to use the cross-entropy loss as the loss function, which is commonly used for multi-class classification problems. Next, we set up the atom optimizer with 0.001 as the learning rate. It is used to update the model parameters during training. And let's train the model for 5 epochs. The main training loop iterates through the specified number of epochs. We initialize 2 variables, train loss and valid loss, to 0 for storing the training and validation losses of each epoch. Also, another 2 variables, train corrects and valid corrects, are initialized to 0 for calculating accuracy after each epoch. The first nested loop iterates through batches of training data. Images and labels are moved to the specified device. The model is used to make predictions or outputs. The cross-entropy loss is computed between the predicted and true labels. The optimizer gradients are set to 0 before starting to do backpropagation. Backward propagation is performed to compute gradients. The optimizer is used to update the model parameters. And finally, the training loss and the number of correct predictions are updated. The second nested loop iterates through batches of validation data. Following similar steps as in the training loop, but without performing backpropagation. After each epoch, the average training and validation losses, as well as the training and validation accuracies, are printed. After correcting some of my mistakes, let's see how our model performs. As we can see here, the train and validation losses are 0.0157 and 0.0276 respectively. The model performed 99% accurate on the train set and 98% accurate on the validation set. Although the results show our network is slightly overfitted, the overall performance is great. And that was a short tutorial on how to create and train your first CNN using PyTorch. I've just started my channel and this is my first video, so I would really appreciate your feedback and comments on how to improve it. Thanks for watching.